would like to introduce Richard Steenbergen, perhaps better known as Raz, who will be presenting Inside the Hidden World of the Pluggable Transceiver. Richard is the Chief Executive Officer at Petabit Scale. This is Richard's 36th time presenting at NANOG. Richard's first time speaking at NANOG was on a panel discussing XSP security vulnerabilities at NANOG 34 in Seattle in 2005. Welcome back to NANOG, Richard. We are certainly happy to have you back with us today.
Hello. So I'm doing a talk on kind of the inside world of the pluggable transceiver that most people who aren't in that space don't see or know anything about. Just kind of talk about some of the cool parts of it. So what's actually inside a transceiver when you take the case off? So there's a couple of key components. There's the optical subassembly. So you have, you see here the example of the TOSA, the transmit optical subassembly, the receiver subassembly, and if you have a co-package, like if you have a single strand optic, it might be a bidirectional subassembly, but those are where all the optical components kind of live. But I'm not really talking about that part so much as I am about the management functionalities and capabilities of the transceivers themselves and the modern protocols and what they do and how they work with them. So there's a management CPU. So these days they're a little ARM. Like little Cortex, M4s, for example. They're little processors. And then there's going to be some other integrated circuits. So the really common ones are retimer, a DSP of some form, potentially, or a gearbox if you have to mesh the different lanes, different speeds together. So there's a couple the historic management standards that you need to know about. So historically, this was all governed weirdly enough, under the Storage Network Industry Association. So in the world of GBICs, SFPs, and QSFPs. So the ones that really matter, the ones that kind of govern the whole world that we live in are SFF 8472. So really the way to think about this is everything that involves a single lane optic. So what originally started for SFP became SFP Plus, became SFP 28, 56, 112. There's very little that actually changes when you change the data rate of the transceiver itself. It's more about the structure. So it's that same physical form factor that's containing one lane. And as you increase the speed, very little changes. So they just update the version slightly, but it's essentially the same thing. So it all ends up being governed by one kind of standard. The other one, so it started out as 8436 and became 8636. Was everything QSFP, so everything 4-lane based. And there's obviously all these other variants, Zenpaks of the world and things like that, but these are the ones that still matter today that kind of that you interact with. And the way that they did this was if you implement 8636, you're backwards compatible to 8436 optics. So you really just have to implement 8636. That's all of your 4-lane optics. And then there's a third standard that really matters that has all the common bits, the bits that are generic to interacting with the transceivers, or the definitions of the protocols, the IDs, the definitions of, well, this bit means that we're talking about a GBIC versus an SFP versus a OSFP. And it all gets broken out into 8024. And this really has become kind of a standard for a lot of stuff. But then there's a new modern standard. So where you're going to find is something called CMIS, the Common Management Interface Specification. So this was really the first true ground-up rewrite of the management protocol since the GBIC. So if you look at the standards for the SFP and QSFP, they're pretty similar, and they're pretty, they keep tacking on updates and extensions and updates and extensions. This is the first complete ground-up rewrite, and it tackles a few things, right? So one is it natively addresses all of the modern 8-lane optics. So in the modern world, if you have a QSFP DD or an OSFP, that's an 8-lane optic. It's 8-lane electrically for sure, and it might be 8-lane optically. So you actually have to update the standard to accommodate that. And they actually thought ahead and made sure that it could scale up. So it uses what's called a banked design. So you have, if you only work with the standard 8 optics that we deal with today, you can live entirely in bank 0, but you can just repeat this over and over and over, and you can address up to 32 lanes. God help us, I hope we never make a 32-lane optic, but it's there in the protocol, just so you don't have to go back and update that. One of the really big design parameters around CMOS is to the seamless support of a new transceiver. So if you're running code on your router that's 2 years old because it's stable, and you need to add a new optic type that didn't exist 2 years ago when that code was written and that was certified, CMOS is really the industry's attempt to put enough information in that transceiver and in that management standard that you have a real shot of being able to do that. So it's a massive overhaul of nearly every part of the management standard. It's essentially 10 times the size if you read the documentation. It's 10 times the size of the EEPROM. It's 10 times the size of the document. It's massive. But once you've used CMOS, you go back and look at the other stuff and you wonder how these things ever worked in the first place. So the history of CMOS, there's really only 3 versions that matter, so don't ask me why they started at 3.0. But 3.0 was the initial release, so this was your very first generation 400 gig optics. And they did a pretty quick follow-up to 4.0 that was incompatible with 3, so they made a bunch of design changes. And there's still a huge number of optics that are out there that are 4.0. And then there's another major version change it's not as incompatible as 4 was to 3, but it introduced some incompatibilities. And then everything since then has been minor increments. So you see it's actually gotten pretty stable. The latest change was 5.3, and 5.3 actually added quite a bit compared to like 5.0, 5.1, 5.2 were very short, quick incremental fixes. 5.3 adds quite a bit, but it doesn't introduce any incompatibility, so it gets to stay in that version 5. And that was there's currently no plans for a 5.4, so 5.3 added quite a bit. But when you interact, a lot of people talk about the EEPROM of the transceiver, and it's a block of memory that you look at when you're talking to the transceiver. So if you've ever dealt with compatibility coding, you're like, oh, we need to recode the EEPROM so that this thing. What's happening here is the EEPROM is your window into the transceiver. It's a block of memory. In reality, it's not even real. It's not actually an EEPROM. It hasn't been an EEPROM since the GBIC. It's almost never a real EEPROM. It's a virtual emulated EEPROM. But it's a block of memory that you can look at. So the host device can read from it and get parameters, get status. It can write to it, set parameters, set things that it wants. And this is the world this is how you get inside the transceiver and interact with it. So what does that actually look like? Basically, the current standard is a 256 byte window. So the first 128 bytes is fixed. It's always going to stay the same no matter what you're doing. And this is your real-time status. You want to be able to immediately tell if a link goes down or something like that. So the first 128 bytes are just that very, very basic real-time status. It's called lower memory. And the upper 128 bytes are paged memory. So every time you want to look at something different, you have to make a request. You say switch to page 2, and you wait, and it will populate page 2. And you come back and read it and do something with it or write to it. But you have to wait for the device to swap out the contents of that 128 bytes. And this is still, in fact, the way that optics are interacted with. This is very, very ancient technology, but that's how you interact with them. So this is what things look like when you try to do transceiver identification pre-CMOS. This is very, very, like the large numbers of fields that are very obscure, and it's really hard to tell exactly what's what. If you put in a new optic type, you are in no way guaranteed that you're going to be able to support it, know how to work with it, if it's something that you didn't design and test for. And if you actually have ever looked at any of the source code behind some of this stuff is hard-coded in like crazy. Like vendors test and design for their optic, and they really don't do that much testing and effort for all those other ones, because it's a huge amount of effort. And so this is an example of what that would look like. We actually start to look at, well, what are these individual things saying? Well, we have a bit that tries to represent if it's this or that, or if it's Ethernet or InfiniBand. It's really, really hard to make this extensible. And they've added, time and time again, they've added all of these extensions. But here's what it looks like in a modern world. So this is what you see out of 8024, and this is every protocol has a definition in here. So this is an example looking at the definition of media protocols from single mode of just one tiny snapshot. So if you're looking at a 400 G-base LR8 optic, you have a very specific type. You have a byte code that's going to tell you this is exactly what it is. You're going to know what the baud rate is. You're going to know if it's PAM4 or if it's NRZ. You're going to know what the lane count is. You're going to know what the bits per symbol is, and it's all very well defined. Not only that, but the host itself is well defined. So people don't think about a transceiver. It's a media converter, and it has two sides. It has one side electrically going back into the host device, and it has one side going out media. But every host has its own standard protocol. So when you turn up a 400 gig DR4 optic, if that's a QSFP 56DD, it's using something called 400G AUE-8 is the electrical standard for that, and that's going to differ depending on if that's a 4-lane, so like a QSFP 112, a 4-lane 100 gig versus an 8-lane 56 gig. That's going to have a different protocol, different standards. There's all these different, there might be different versions for different lengths, whether it's a long distance run or not, or whether it's equalized or not. But the way CMOS works, the way that this works, that you can kind of do all of this support for future-looking protocols, is what's called application selection. So CMOS actually explicitly defines every supported application that you could be working on. So I think I actually started writing this on the plane and didn't actually go back and update the bytes. But this is an example, right? So if you look at an optic, it's going to say application 1, and it might be, here's a 400 gig to a 400 gig DR4. We can break that out into 200 gig lanes. We can break that out into 100 gig lanes. But it might also have, for example, we can support InfiniBand. We can support other protocols. And the reason you have to do that is the chips themselves, the retimers, are actually, there's different chips and they have different capabilities. And they're actually going to put in a different chip depending on your needs. And interestingly enough, it turns out it's not really because the chip is any more expensive. The reason that they might make an Ethernet-only version as opposed to an Ethernet InfiniBand combination version has to do more with the length of time that it takes on the QA test cycle. If it supports more protocols, they have to test it for longer. That really drives up the production time and cost. So you literally have an explicit spell out of what these things are, and you pick from that as the host device so that you know what's going to be supported. So you might have one version that doesn't support 4x100 gig breakouts. You might have one that does, and it's going to be explicitly spelled out in the CMOS application selection what that is and what it's capable of. So here's an example of a real life pull off an optic looking at an FR4 and showing that, and it's going to be encoded as the byte itself. So that byte is going to match up to one of those 8024 entries. So you can go look it up and see exactly what it is. And it's going to tell you how many lanes that is. And there's going to be a lane mapping. So it might tell you, for example, if you're capable of mapping lanes 1, 2, 3, and 4 to one thing and lanes 5, 6, 7, 8 to another thing. It's going to describe that for you very simply. So another major thing that CMOS introduces is something called VDM, Versatile Diagnostic Monitoring. So this is a complete, if you've ever used, if you look at the light levels on your optic, that originally started out as something called DOM, Digital Optical Monitoring, became more generic DDM, Digital Diagnostic Monitoring. That was the very first generation of monitoring support that was built into optics. And it really tells you very basic things like transmit light levels, receive light levels, a laser bias, voltage, and then they tacked on a few more things, but it was very, very basic. So with CMOS, they introduced VDM. It's a complete ground-up rewrite of the monitoring capabilities of the optics. So you can actually now have, because you have little sophisticated computers on these things, the optic itself can collect telemetry over time. It can monitor that in, in 10 millisecond increments and build a compiled set of data for you and then hand it over to you on occasion when you need to. It can look at it much faster than you would ever be able to on its own. And it's capable of doing a huge number of things. You can look at You can get these very sophisticated signal analysis. You can look at the PAM4 transition levels and eye closures and stuff. And I think I actually loaded the wrong slides in here, but so cool things that VDM introduces, there's something called laser age. It's not so much laser age as it is laser health. So basically they give you a 0 to 100 rating of the health of your laser. And you used to be able to figure this out. You could look at the laser bias, the electrical draw, and the transmit power, and you could figure out, you could see the signs of an optic that was going to fail. Well, they essentially turned this into a health status. So you can look at your laser and you can see as it's on its way to failing, weeks or months before it fails, you can see it start to decline. Pick that up. But you can also look at things like prefect bit error rate. So a lot of people don't understand that in a modern optic, everything is so driven by FEC that FEC hides, as error correction, FEC hides all of the potential failures that you could be right on the edge of failure and still have a completely clean signal and not know about it. You don't know about it until you cross that cliff. So if you aren't looking at your prefect bit error rate, you have no idea if your optic is really, really good with lots of margin or about to die as soon as some tech comes and jiggles the cable. And a lot of vendors actually are not exposing this in the switches themselves. So you have a lot of cases you have to go to the optic to pull these stats. Well, the nice thing about these optics is they actually monitor these stats for you. So you can look at the SNR, you can look at the prefect bit error rate, and you can see the status of a link. But it's still, I think Arista is probably the best in the space as far as exposing this. And a lot of other people are still playing catch up on that. There's other cool stuff that you can do. So you can do bit error rate testing. These optics are actually capable of generating the PRBS, the pseudo-random binary sequences. So you can plug in a 400 gig optic, and just built into the optic, it'll generate a 400 gig test signal that you can send out over the fiber and read back and look for errors on the line system, errors on the fiber, test the optic itself. All this stuff is built into these optics now. There's a thing called the command data block. So this is where they started introducing capabilities. So it wasn't in the very first version. It was in the 2019 version, CMOS 4. But this is where you do really complex transactional things. So imagine the biggest example being firmware upgrades. You can now take your transceiver and you can flash new code onto it and change its functionality. And you didn't used to be able to do that before. You have to send it back to your manufacturer or just throw it away and get a new one. And all they're doing is changing the code that's running on that little microprocessor. Well, now you can actually reflash that yourself. The problem being these are pretty big images. You might have a half a megabyte file that you need to push to your transceiver. Imagine trying to do that through that little 128 byte window. So they wrote an extension to this called CDB, the command data block, and this is where you do all those big transactional things. So you can now do firmware upgrade, downgrade. There's an A and B image. You can test one out. You can commit it once it's done. You can roll back to an earlier image if it doesn't work out. They've really baked all of this in for that real scale and extensibility into the design of the optic itself. You can do the high volume transfer of performance metrics, so stuff that you wouldn't have been able to collect before, very large bulk data from the transceiver, you can now do. And here's one that a lot of people don't know about. So there's a password if you actually want to make changes to the transceiver. But there's not actually a command to verify if you got the password right. So what you have to do pre-CMOS, pre-CDB, was make a write and then read it back and see if the write took. So like you overwrite the vendor name or something and then like restore it if you got it right. So CDB introduces all kinds of really cool things in that space. So here's some examples of what those commands look like. Here's what did I do here? Like here's the module capabilities command. So you can issue a command and say, tell me all the module features, and it'll tell you lots of details about what it's capable of and what are its timeouts. How fast can you interact with it? What are the different problems? Does it have the AB image support? Does it have the ability to do all these different things? You can look at the firmware itself. You can look at the performance monitoring capabilities. You can look at the BERT diagnostic features, and it will explicitly tell you in these very well-defined structured messages what the optic's capable of. And they're now adding new security features as of CMOS 5.3. So like here's an example of when you actually look at the module features, and you can see like, well, what is the max duration that the optic might be doing something before I can talk to it again. Is there a copy command? Can I copy the firmware from slot A to slot B or not? That was an optional implementation. Can I abort something that's in the process? Can I, what payload sizes can I send for different messages and different types? And there's all these different ways that they've been adding and adding and adding to interact with the optic, and it's all these very well-defined messages. And it's a pretty complex upgrade process, right? You have process where to make this easier, it might like auto advance a page, or it might have a big block of extra memory that you can write to, where you can do these big byte transfers. But this just kind of gives you an example of what that looks like. But what's actually on the firmware? So people a lot of times get confused when they talk about the EEPROM and the firmware. Well, what is the difference? So remember that EEPROM is an artificial construct. It is there for you to look at and read a status. Is the link up or down? Is the electrical signal good? Is the cooling system turned on or not? What is the light level? Or to talk to it, turn the port up, turn the port down, turn on the equalizer, retune the laser. But it's that interface. The firmware itself is actual code that's running on these systems. And the cool thing about it is, because they're little ARM cores, you can actually decompile, reverse engineer these things. There's a bunch of open source tools. So here's an example of a hack that I did while I was debugging something goofy from Finisar. There's an open source tool called Hydra, released by the NSA, that you can load these firmware images up, and actually got a virtual emulated optic running on my laptop, and you can see it like talking to its virtual EEPROM, running, sitting along there running, and you can actually see everything that it's doing, look at all the strings, all the messages. There's some pretty cool stuff. So here's an example of that. So it was a 512 byte binary, but what's actually in there, so it's 380K of image. About 80% of that is the microcode that gets loaded on. So for example, all of these modern 400 gig optics, or everything that's 100 gig single lambda based and above, all has a DSP in it. You have to load a microcode. So when you plug in that optic and it powers itself on, you transfer the microcode into the DSP, you boot it, you run it, and that's what's living in that firmware image. That's making up the vast majority of this. And there's very basic Linux tools that you can look at these binary images and see exactly what they are and how to work with them. So where do you find CMOS? So this is where things get a little bit weird. There's a realm where 100% you're guaranteed. If you're dealing with an 8-lane optic, so if you've got a QSFP DD, if you've got an OSFP, if you've got anything that has XR8 in it, for sure you are dealing with an 8-lane optic. So all your 400 gigs, originally all your 400 gigs, all your 800 gigs, everything higher than that. If you were dealing in traditional single lane or 4-lane optics, it was all like, they wrote extensions, you can use CMOS in it, but it's not very common. So the big gotcha is like 200 gig, for example. 200 gig can be done either way, like a QSFP 56 200 gig. That can be done either way, and there's a lot of vendors that went one way or the other and just didn't implement the other because it wasn't in the optics that they sold. So that's where it gets a little goofy and weird. But then you start to see, for example, now as we come full circle back to QSFP 112. So this is now a regular QSFP that only has 4 lanes. You could technically implement it in 8636, but it's that new enough threshold that no one's writing for new optics in that. They're going straight to CMOS for everything. But this is kind of the chart that shows where CMOS is deployed and where you're able to interact with it. So here's some of the examples of new things that they're adding in 5.3. Actually, I meant to add more slides on this, but the way that we interact with the optics today is just straight I2C. So it's very, very basic 2-wire interface. It used to be called TWI. They've renamed it, so it's now MCI, the Management Communication Interface. So as of 5.3, they actually added SPI support. So you're now able to work with the optic outside of that. I don't know that anyone's actually deploying this in real production yet, but it's in the standard now that you're able to work at much higher speeds. You're able to work with much larger blocks of memory and not do this 256 byte virtual EEPROM window. So you can kind of address anything that you want. And they added a significant number of commands in there. So what can I do with this? How can I interact with this? What fun stuff can I do? So a lot of vendors are out there trying to block third-party transceivers. And there's a cynical take of this that says they do it because they want to protect their profits, and there's certainly an element of truth to that. But in reality, if you've ever tried to, from the vendor side, support pre-CMOS, it was incredibly difficult. It's incredibly difficult to get that coding exactly right. It's kind of a miracle that things ever worked at all as well as they did. And even in CMOS, it's not a complete perfection. So what would really be nice is if we had a white box open source firmware for these things. And the reason that we don't is that microcode. So that microcode is kind of locked down exclusive license of like a Marvell or a Broadcom, and they don't want that being out in the wild. But there's hyperscalers that have actually written their own transceiver firmware, so they're not dependent on the vendor. And they know what the chip is. They know if it's a Marvell or Broadcom chip. They have those relationships that they can get that code themselves. But there's an example of hyperscalers who have done that. But that would, if that ever comes to pass, that would unlock the capability to really have a known, guaranteed working optic that wouldn't be dependent on that code. But a lot of these vendor locks are really easy to defeat too. So for example, if you want something to be compatible with Arista networks, all you have to do is write in ASCII Arista networks to the vendor name. If you want something to be compatible with Mellanox, actually I think I loaded the wrong byte in here because I was writing on the plane and didn't go back to fix it. You write the vendor OUI of something out of their table into the vendor OUI field. It's really easy to defeat a lot of these things, and it's stuff that you can do yourself very easily without being dependent on a third-party programmer tool. So the basic administrative stuff, these are the ones that when you reprogram an optic, this is like the most basic of basic stuff that you care about. It's very simple fields. There's a 16-byte field for the vendor name. There's a 3-byte field for the vendor OUI, vendor part number. And these are just straight ASCII. And if there's anything after, it's padded with space. So you just write 20 in hex. And there's a revision serial number, a date code, CLEI code, and the module power capabilities is one that you can override. So if you want to turn up an optic that takes 3.5 watts and you're putting it in a NIC that has a hard cutoff at 3 watts, you can just recode that thing to say 3 watts and it'll still work just fine. Because they tons and tons of redundancy is built into these specifications in these systems. So you can usually push it a little bit further and still make it work. So here's some examples of things that are safe. So if you've worked with Sonic, there is a Linux kernel driver that came out of OCP Works, something called Opto, and it turns the EEPROM, the transceiver EEPROM, into a flat file. So there's literally sys bus I2C devices. You can find a little EEPROM file and you can just write to it. You write to it in the correct places, and that is interacting with the optic. And it's going to take care of all the memory paging, locking, all kinds of stuff. So I was going to toss in some like simple tools in here, but there's a bunch of open source tools that you can find to just straight write to these files, and you can do a lot of this reprogramming of optics yourself in an open source. Any white box switch that runs Sonic, Cumulus, same interface, has this capability. An example of something that's unsafe. So Junos Evo, when they rewrote this, it's literally just a Python wrapper around Linux I2C tools. So they don't actually they have an expectation that they're going to turn off their polar when you're interacting with the optic doing something else. And if you don't do that, if you leave their polar running in the background, you can get a really nasty race condition. So I've run across people who have done this and screwed themselves, causing links to flap randomly because they're trying to, they run a cron tab and try to talk to an optic at the same time the polar's running in the background, and it's changing the memory pages out from underneath you. There was a whole bunch of tooling around this that I meant to add more. I meant to add more stuff around, but there's a lot of capabilities in this space that just I really wanted to talk about, and that's pretty much the gist of it. But lots and lots of time for questions.
Thank you, Roz. There's some great information about a topic we don't normally hear a lot about. Does anybody have any questions for our speaker? Oh, yes. Please remember to introduce yourself and the company you're representing before asking your question.
Robert Davis with Myriad 360. As the versions evolve, 5.1, 5.2, 5.3, what do you feel is the impact to cost of the SFP to in good faith, implement all of it. Because I assume they're just available feature sets, not necessarily prescriptive, you must do this.
There's definitely a lot of complexity that got added, but I would say that it's all good complexity. It's all stuff that really made the things more reliable, more featureful. It made it, you don't have to guess. You don't have to like have a secret implementation that no one knows about. It is well spelled out in the standards, all the way down to the name of the variables in the different fields. They did a really, really good job of documenting this. So it ends up being a 400-page document just for the core portion of CMIS. But it really makes life so much easier to work with that literally once you've done that, you go back and you look at the other stuff and you legitimately wonder how it ever worked at all. It's that much of a difference. Anybody else? All right.